But at billions of Gs, even a beam of light feels the gravity and begins to bend back on itself. Curiouser and curiouser. Such a place, where the gravity is so large that even light can't get out, is called a black hole.
Welcome to Decoding Packets Service Provider Technology series. Today's topic is from the realm of BGP security, Introduction to Remotely Triggered Black Hole Filtering, or RTBH. In this video, we will talk about what is RTBH and why is it even needed, and the two flavors of RTBH, destination-based and source-based. Well, on to what is RTBH and why is it used. So the purpose for RTBH's existence first. It is a technique that can be used to mitigate denial of service or distributed denial of service attacks. Now, what distinguishes it from other techniques is the ability that it imparts the network operator to drop or filter the offending traffic at the edge of the network itself, so before it enters the network, which is highly desirable. Now, it is usually applicable within a single AS, which is normally your service provider AS, but the technique itself can be used to implement filtering between ASs. It's pretty scalable, but as long as they have a pre-arranged understanding. So, what do we need in the infrastructure to implement this? Well, the technique depends quite heavily on two main BGP principles. Firstly, it utilizes the BGP next hop attribute, but when we say that, we are really leveraging the BGP route recursion process to our advantage, as we shall soon see. And secondly, and optionally, it can use the BGP community attribute as a signaling mechanism between the BGP peers. This is also explained soon. Furthermore, there are two different flavors that this technique offers us. An implementation that essentially takes the victim offline, no longer reachable by the attackers or at all, which you will see is a major side effect of this flavor. This is called the destination-based RTBH. A second implementation actually blocks the attacker, which means any traffic source from the attacker IP is no longer allowed to enter the network. This is called the source-based RTBH. It is time to flesh out some of the concepts mentioned so far, and first up is the BGP next hop attribute. This is probably so familiar to most network engineers and operators that they don't even realize it exists, or at least that it exists explicitly, but exists it does. And furthermore, at least for IPv4 and IPv6 NLRIs, it happens to be an IPv4 or an IPv6 address. Observe this excerpt from a BGP update packet that was captured on the wire. Clearly, in this particular update, which happens to be for the IPv4 NLRI of 100.100.100.0, the next hop attribute was 4.4.4.4. As one can imagine, this attribute absolutely affects the installation of this NLRI, or the route, colloquially, into the forwarding information base, or the FIB. For those familiar with IGP route installation, the process here with BGP is marginally more involved. To install any route into the FIB, the router must figure out an exit interface. With IGP routes, this is fairly easy. It is the interface where the router received the particular update. BGP, not so much, since if you can imagine, at least with iBGP, the NLRI might have been received on any of the many interfaces. Therefore, an additional process takes place on the receiving router. The router essentially does another lookup on this next hop attribute address, IPv4 or IPv6, and must find a local route. That is a route in the local FIB that in fact points to an exit interface. Now, this process is usually not very clear from the output of the RIB, which for BGP, depending on your implementation, may or may not show the entirety of the information. See, nothing about where the traffic might be sent. To view that information, one must observe the forwarding information base, or the FIB. There. Much better. Now you can see that the router has performed another routing lookup, or a recursive routing lookup on 4.4.4.4 that led to a directly connected next hop. This is the information. This information in the FIB is the information based on which the layer 2 frame can and will be built. So for the purposes of this video, just remember that the router keeps performing this lookup on the next hop information recursively till it can find an actual exit interface. And then it proceeds with the installation of that information into the FIB. Next is the concept of discard route and how it can apply to a BGP NLRI. A discard route, usually a static route, essentially drops all the traffic mapped to it in the routing table. Now, depending on the implementation, it is sometimes called a null zero route, a discard route, but very generally, it's also sometimes called a bit bucket. But essentially, all the traffic that is mapped to that route is dropped. To achieve the same behavior for BGP NLRI, there are two methods available. Number one, it can be done programmatically. So essentially, you're just instructing the router to drop the traffic for that NLRI regardless of the next hop attribute. So you do it via policy. This option usually would be found in SP grade implementations. So Junos, iOS XR, they're good candidates to have this available. The other method is time-tested and should be available for most, if not all, implementations. For that method, we have to first realize that the next hop attribute is just like any other attribute, say local preference or origin. Just like a local preference of a route can be changed, so can the next hop. So essentially, alter the next hop of the NLRI in such a way that it resolves then to a local route, recursive lookup, that is set to discard packets. In this example, which follows from the last slide, the next hop of the router, or the next hop of the NLRI, in fact, has been changed to an address that points to a discard route. Therefore, this BGP route, if you look at in the FIB, this BGP route is now as good as a discard route. Next up, the BGP community attribute. Now, this is an optional transitive attribute, which essentially means that a BGP speaker does not have to understand it, but if the NLRI is advertised to another, then this must be included within that NLRI. Now, in 2019, the year of this particular recording, it would be very surprising if any BGP implementations out there do not understand the community attribute, but technically it is optional. Very simply, a community attribute contains a numerical value. The length of this value depends on the type of the community carried. Now, standard communities would be 32 bits long. Extended communities would be 64 bits. The purpose of the community attribute is simple. It is to group together disparate NLRIs that still need to have a common policy applied. So for example, you can apply a certain community to all of the routes that must have their local preference altered to 500. Now, one must realize that there is no universal community that does this automatically, that, hey, tag your routes with something like that and it'll automatically change. What needs to happen here are several steps. So the operator first needs to decide what that value must be. So are you willing to support a value that provides this kind of behavior? So suppose the operator selects 1:500. Next, the operator needs to create a local policy on every BGP speaker that this needs to be applied to. So most customer-facing BGP speakers, they must have this policy applied. Now, the policy would be to look for that community attribute in a received NLRI. So if a customer advertises you an NLRI, look for that community attribute. If detected, change the local preference of the NLRI. So you're using the community in the NLRI, but ultimately you're changing the local preference attribute. And you would change it to 500 or whatever is your agreed upon value. Ultimately, the operator must share this information with the customers who will then utilize this community value. So now, if the customer has 2 routes, one of them can be based on the default local preference, but it wants to give another route maybe higher preference. So maybe the default local preference is just 100 normal. But some routes, similar looking routes, they need to be at a local preference of 500 or more preferred. Then they can tag those particular routes with that particular community agreed upon before, and their local preference would now automatically be changed. Another example, now this one is much more relevant to our topic, is the local policy can use the community similarly to alter the next hop attribute. So just like in previous example, we altered the local preference attribute, we can alter the next hop attribute just as easily. So what do we want to do with that? Well, we want to make sure that the NLRI becomes a discard route. So shared with the customer, any routes now tagged with this community will cause the provider router to drop traffic mapped to that NLRI. Don't worry if this is not gelling yet. The video will spend significant time on this. Finally, BGP has some well-known communities. So these communities have known names, so well-known associated names, and also a well-known associated value, and finally a well-known associated behavior. The idea behind well-known communities is that the BGP operator, they should not have to define custom policies for these. So just like the last 2 examples, the operator had to go and define custom policies. For well-known communities, that behavior, the name and the value, should be baked into the OS implementation itself. There are a few of these, but the only one relevant to RTBH is called the no export community. A route or an NLRI tagged with the no export community must never be advertised to a pure eBGP peer, right? So if a BGP speaker receives that NLRI, it can advertise that NLRI to any iBGP peer. So this would be in case of route reflectors, or confed eBGP peers. So within a confederation, but not to a pure eBGP peer. So what is the effect of this? The effect is you're restricting the route from leaking outside the AS. For something as radical as RTBH, where you're trying to drop traffic, this community is very beneficial because you want to restrict that effect within your AS. And the no export community is going to be very useful for this. Now, we have the basic conceptual building blocks of RTBH. Now is a good time to talk about the first implementation, the destination-based RTBH. This is the original implementation of RTBH. So, like we discussed before, in this flavor, all traffic mapped to a particular destination or a particular network can be dropped. Now, as you've probably already guessed, via a BGP discard route. Typically, this particular destination or the network would be where the victim of the attack resides. So it is the actual victim or it is the network that has that victim. So for this reason, for RTBH, most service providers would accept routes that are longer than /24. So usually there is a restriction of not accepting very long routes, but for RTBH, there is an exception to this. So this allows the customer to signal discard routes for specific victims even, /32s, without affecting too many other hosts on the same network. That brings us to the next question. Who will originate such a route? Well, the answer really depends on SP policies. The SP can allow the customer to signal such a route. Of course, the SP would have to ensure that the customer has the authority, number one, to signal that route, so they're not advertising somebody else's route and blackholing their traffic, so they are only advertising a part of their own owned IP addresses. And the next thing is they would declare an RTBH community, they would create the policies, and they would share that RTBH community with the customer. So now when the customer advertises a route with that RTBH community, that traffic would be blackholed, or traffic to that destination would be blackholed. Don't worry, we will demonstrate this in action fairly soon. Alternatively, the SP can set up a dedicated trigger router that can originate the NLRI. So instead of having the customer signal it, you can have a trigger router within your AS to do this for you. So the idea now is that the customer calls the NOC, right? So either you place a call to the NOC, or you go to the web page that has been set up for this particular purpose, authenticates themselves, and then requests the SP to blackhole that traffic or a network. Keep in mind that the customer will use communities to control this process, while the trigger router has multiple options. So it can alter the next hop at the origin to something that is assured to be a discard route at other BGP peers, or it can also use communities. So both of these will be demonstrated next as well. Now that we have discussed the particulars of destination-based RTBH, let's look at a possible scenario where this might be put in action. So this is a fairly common SP network setup. You have a few ASPRs that face the internet. You have a PE router that faces the CE router, and behind the CE router may be a victim, so a single machine that is being attacked. And it is being attacked by, let's say, a good guy in green, and then a bad guy in red. So they're sending green traffic and the bad traffic. The red traffic, it goes to the ASPR, it makes its way through the SP network, and it is finally going to affect the victim. So there are a couple of ways where we could stop this, and as we have discussed, this is either by using the static route. So you would use you would alter the next hop in your NLRIs and then drop it on the edge routers, courtesy of the static discard route. Or you can use just a BGP policy which looks for a community. So let's discuss the first one of these first, because this probably would be the most common implementation within a single AS. In this particular case, the CE or the customer realizes that there is a victim under attack. Now, once they identify the /32 address of the victim, they're going to start advertising this address to the PE. But before they advertise it to a PE, they're going to make one very important alteration to it. They're going to attach the RTBH community to this. So suppose that community is something like 666. Now usually it's in the form of something colon something, so it's a 32-bit number. It would be something like AS colon 666, and you're assuming you have just a 2-byte AS and not a 4-byte AS, but something like that. Just imagine some arbitrary value that identifies the RTBH community. Once this NLRI is advertised to the PE must have a policy that then changes the next hop, alters the next hop of the received NLRI to something pre-decided. So suppose in this case we decided 172.0.1 or actually 2.1. So why that particular address or that particular range? Well, this is the test net address. It is supposed to be any addresses in here, 192.0.2/24. They are supposed to be used for documentation, example code, things like that. But the original RTBH RFC suggests the use of this, and it is fairly commonly used as well. So ultimately, the next hop is altered. Once the next hop is altered, the PE is then going to advertise this NLRI to all of the ASPRs, the edge routers. Whether this is done via a full mesh, whether this is done via route reflector configuration, that is not relevant to our particular scenario. All we need to make sure is that it is in fact advertised all the way out to the ASPRs. Now, the ASPRs must have a static discard route already programmed on them. So 192.0.2.1 on these ASPRs must point to a discard route, or must be treated as a discard route. So on iOS routers, for example, you would point it to null 0. On Junos routers, you would create a static route that has the next hop of discard, or reject, but usually discard. So now when the BGP NLRI is received on these ASPRs, they're going to install it into the FIB. And when they install it into the FIB, they're going to recurse down to this route, if everything goes well. So that received BGP NLRI now essentially becomes a discard route, and you start dropping traffic on all of your edges. So effectively, you've taken the victim down. So it is no longer reachable by the attacker or anybody else, which, like I said, was a major drawback of this particular scheme. Another way of doing this, so instead of the customer signaling this directly, you could do it via a trigger router. And in this particular case, usually the customer would then either place a call to the NOC, or in 2019, they may have a web page that is set up for this. To that web page, they would supply the same /32 address. They would authenticate themselves. They would make sure that they're allowed to advertise within that range. But ultimately, it's the same step as before. The NOC then takes that information to a dedicated RTBH trigger router. Now, this could be a centrally placed route reflector, but ultimately it could just be a dedicated RTBH trigger router. But what needs to happen then is that this RTBH trigger router needs to originate this /32 once again with the next hop altered. Or if it's originating, then it could from the start have the next hop defined as this 192.0.2.1 address. The final effect is absolutely the same. So instead of the PE receiving that route and re-advertising it to everybody else, the RTBH originates that route, the trigger router, and it advertises it or reflects it to all of the other ASPRs. Final effect, absolutely the same, courtesy of the static discard route that already has been placed on those routers, and the traffic is dropped. The other way of doing this would be to use the RTBH community all the way out to the ASPRs. So this time, let's just do it for the CE again. The CE advertises that /32. It is tagged with the RTBH community. But the PE, instead of altering the next hop, just makes sure that, does all of the checks on the advertisement that the victim is authenticated and the CE is allowed to advertise that. But unaltered, but with the RTBH community, it advertises it out to the ASPRs. Now the ASPRs must have now a local policy configured on them that is doing the same thing that the PE was doing in the first place. So it is a local policy that looks at the RTBH community and then makes sure either programmatically, so like I said, on iOS XR and on Junos, you could literally change the next hop to discard, or you would change the next hop to that static route, but ultimately the final effect that you're looking for is that that received route becomes a discard route. What is the benefit of using next hop alteration versus the RTBH community? Well, think about inter-AS signaling. So if you have two separate ASs and maybe two separate providers, so inter-provider, inter-AS, In that particular case, they may not be able to agree to a static route that both of them agree is going to be the RTBH route. In that case, they can instead agree to a community. And that community then can be signaled between the two of them. And once they make their checks, they can finally start dropping that traffic. That happens to be all for this time, but in our next video, we will close out the topic of destination-based RTBH with a live demo. Till then, I hope you've enjoyed this video and are looking forward to the next one. Thanks.